Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Augustin Louis Cauchy's 1847 publication, Celeste Fonctions continues, represents a pivotal moment in the rigorous formalization of real analysis. This work, though seemingly narrow in scope, addressed fundamental questions about the nature of continuity and differentiability of functions, concepts which, at the time, lacked the precision necessary for building a consistent and reliable calculus. To fully appreciate Cauchy's contribution, one must first understand the state of mathematical analysis in the decades preceding his intervention. Prior to Cauchy, the calculus, while immensely successful in solving physical problems, rested on shaky logical foundations. Mathematicians such as Newton and Leibniz had developed powerful tools, but their justifications often relied on intuitive notions of infinitesimals, quantities considered to be infinitely small yet still non-zero. This approach, though fruitful, led to paradoxes and inconsistencies that troubled many mathematicians. The notion of a continuous function, similarly, remained largely intuitive. It was a function whose graph could be drawn without lifting the pen, a description useful for visualization yet inadequate for rigorous proof. Cauchy's project, part of a broader movement towards rigor in mathematics, aimed to replace these intuitive notions with precise definitions based on arithmetic. In Celeste Fonctions continues, Cauchy provided a definition of continuity that, while not identical to the modern epsilon-delta definition, captured its essence. He defined a function f of x as continuous between two given limits when, between those limits, an infinitely small increase in x produces also only an infinitely small increase in the function itself. Although he still employed the language of infinitesimals, his approach differed significantly from his predecessors. He attempted to give infinitesimals a more precise meaning, defining them as variables tending towards zero. The core of Cauchy's approach lay in what he called the infinitesimal calculus. He sought to rebuild calculus entirely on the concept of limits, avoiding the logical pitfalls associated with undefined infinitesimals. Crucially, in his definition of continuity, the infinitely small increase in the function was implicitly tied to the infinitely small increase in the independent variable. This connection, though expressed in terms of infinitesimals, foreshadowed the modern concept of a limit. Moreover, Cauchy introduced the concept of uniform convergence in his study of infinite series of functions. He initially believed that the sum of a convergent series of continuous functions will itself always be continuous. This statement seemed entirely reasonable from an intuitive standpoint. However, this proved incorrect. This assumption, however, led to contradictions, most notably when dealing with Fourier series. Niels Henrik Abel was among the first to point out difficulties with Cauchy's initial claim. This realization spurred further investigation into the nature of convergence, ultimately leading to a sharper differentiation between pointwise and uniform convergence. Celeste Fonctions continues did not present the modern epsilon-delta definition of continuity directly. The later work of Carl Weierstrass refined Cauchy's ideas, replacing the reliance on infinitesimals with the now standard epsilon-delta formulation. In this formulation, a function f of x is continuous at a point c if, for every epsilon greater than 0, there exists a delta greater than 0 such that whenever the absolute value of x minus c is less than delta, the absolute value of f of x minus f of c is less than epsilon. In spoken form, this means that for arbitrarily small changes around the point c, we can guarantee that the function values stay close to the function value at c. This definition provides a precise, arithmetic criterion for continuity, devoid of any reference to infinitesimals. Despite the lack of the modern epsilon-delta formulation, Cauchy's work was incredibly influential. It represented a significant step towards the arithmetization of analysis, replacing geometric intuition with rigorous algebraic definitions. His definition of continuity, coupled with his work on limits and convergence, laid the groundwork for the subsequent development of real analysis. The immediate impact of Cauchy's work was a renewed focus on rigor in mathematical analysis. Mathematicians began to scrutinize the foundations of calculus with unprecedented care. Cauchy's textbooks, based on his lectures at the École Polytechnique in Paris, became standard references, introducing a new generation of mathematicians to his rigorous approach. His emphasis on precise definitions and rigorous proofs helped to eliminate many of the ambiguities and inconsistencies that had plagued calculus. In later mathematicians built upon Cauchy's work in significant ways. Weierstrass, as mentioned, provided the definitive epsilon-delta definition of continuity. Bernhard Riemann extended Cauchy's notion of the integral, creating the Riemann integral, which handled a broader class of functions than Cauchy's original definition. Georg Cantor developed set theory, providing a framework for understanding the nature of the real numbers and the concept of infinity, further solidifying the foundations of real analysis. These developments, while going beyond Cauchy's original work, owed a considerable debt to his pioneering efforts. One could argue that Cauchy's work represents a transition point. He was operating during a period of significant mathematical development. He was still tethered to certain prior notions while simultaneously forging entirely new techniques. His use of infinitesimals, although refined, contrasts sharply with Weierstrass' completed rigorous approach. This very contrast, however, illustrates the historical process of mathematical discovery. The reception of Cauchy's work was mixed. Some mathematicians, particularly those trained in the older, more intuitive style of calculus, resisted his emphasis on rigor. They saw it as overly pedantic and unnecessary, arguing that the existing methods had been successful in solving practical problems. Others, however, embraced Cauchy's approach wholeheartedly, recognizing its importance for building a solid foundation for mathematical analysis. The development of non-standard analysis in the 20th century, pioneered by Abraham Robinson, provides an interesting footnote to the history of infinitesimals. Robinson showed that it is possible to create a consistent logical framework in which infinitesimals exist as actual numbers, vindicating, in a sense, some of the intuitions of the early calculus pioneers. This outcome represents something of an ironic twist, given that Cauchy and his successors worked so hard to banish infinitesimals from rigorous mathematics. The implications of Cauchy's work extend far beyond the realm of pure mathematics. His rigorous approach to analysis had a profound impact on other fields, such as physics and engineering. By providing a solid foundation for calculus, Cauchy enabled scientists and engineers to develop more accurate models of physical phenomena. The concepts of continuity, differentiability, convergence are essential tools for understanding and predicting the behavior of complex systems, from the motion of celestial bodies to the flow of. Moreover, Cauchy's emphasis on rigor influenced the development of mathematical education. His textbooks became models for teaching calculus and analysis, promoting a more precise and logical approach to mathematical reasoning. The emphasis on definitions, theorems and proofs, which is now a hallmark of mathematical education, can be traced back, in part, to Cauchy's influence. Even today, Cauchy's work continues to be relevant. His contributions to analysis are fundamental to many areas of mathematics, including differential equations, functional analysis, and numerical analysis. The concepts and techniques he developed are still taught in universities around the world, forming an essential part of the education of mathematicians and scientists. In conclusion, Augustin Louis Cauchy's Sur fonctions continues may appear, at first glance, as a modest contribution. However, this short paper, published in 1847, was a crucial step in the development of modern real analysis. It represents a conscious rejection of intuitive arguments in favor of precise, arithmetic definitions. Its impact continues to be felt today, not only in mathematics but also in science, engineering, and education. The pursuit of rigor, championed by Cauchy, remains a guiding principle for mathematicians and scientists seeking to understand the fundamental laws of nature and the intricate workings of the mathematical universe. The transition from intuitive infinitesimals to rigorous limit definitions was a hard-fought battle. The echoes of this historical struggle continue to resonate in contemporary mathematical discourse, reminding us of the importance of questioning assumptions and striving for ever greater clarity and precision.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.